Okay, now we're back to looking at center of mass again. The reason center of mass is included in this unit is that it's really the exact same thing as conservation of momentum. Conservation of momentum, center of mass, Newton's third law are really all different ways of looking at and analyzing the same concept. Earlier in the year, we looked at center of mass this way, that the position was 1 over the total mass times the sum of the product of the individual pieces of the mass, and we add up. Now we have a new way, though, of adding up little pieces, right? For this we had to use regular shapes, things like squares, rectangles, triangles. But what if we have irregular shaped objects, or a changing distribution of mass, where something doesn't have a constant density throughout? In that case, we need calculus. So we imagine that this is getting like closer and closer to 0, and what we end up with now, our new formulas, look something like this. Right, so we're multiplying the position by that tiny little piece of mass. Right, it's still a multiplication since we're multiplying, we're adding things up. That's what the integral is about. And so then for y, works the same way. The y coordinate of the center of mass, we get this way. Okay, and we're going to end up with mass densities, different types of mass density. Things like linear mass density, surface mass density, and volume mass density. We're going to see this again later when it comes to charge, because we're going to have a certain amount of charge per area, a certain amount of charge per volume, and that kind of thing. So when you see these symbols, mass, lambda, all these things, lambda is the mass per length, and that is dm dx. Okay, so we're looking at how much mass there is in the length of the whole thing, and what that is in terms of calculus is dm dx. Okay, and then sigma is going to then be mass per area, so that's dm dA. Right? So what are we looking at? This is really, right, mass per length. This is mass per area. So this is going to have units of kilograms per meter. This is going to be kilograms per meter squared. And then rho is volume mass density. So it's dm dV. So this is mass per volume. This is kilograms per meter cubed. What this allows us to do is, if we know the total mass and the total volume, we can put these in here. But if we have a function, some function where the radius is changing, then we can use that function to find what that is as well. And then we can add it all up to get the total mass, or to get rho, things like that. So we may have functions for rho. Right? The volume is actually changing as we go outward, or something like that. Okay, so here we have a derivation, one of these derivations. Here we're going to prove that the center of mass lies in the center of a uniform rod. So first we're just working with a uniform, a rod of uniform mass density. Since we're dealing with a rod, we're going to be using the linear mass density formula. So we have linear mass density is big M over L, and that's equal to dm over dx. All right. Now, if I solve this, I end up with the mass equals lambda times L. Okay, and then also, because each piece of the mass and the length, I have the same amount of mass per length each time, then I know that dm is equal to lambda dx. So now I have these two equations. If I want the center of mass, then I get that by taking 1 over big M times the integral of x dm. Right, this is our formula. Okay, and what we're going to do then is take here, instead of dm, I know dm is equal to this, lambda dx, so xcm is 1 over m x times lambda dx, right? dm is equal to this, so that's what goes in there. So this becomes now lambda over m. Lambda is some constant number, and this is x dx. Right, and where we're going from 0 to L, whatever that length is that we have. All right, so let's come up here now, take the integral, so we have, that's not x, that's supposed to be lambda. Lambda over big M, 1/2 x squared from 0 to L. So this ends up being lambda L squared over 2m. Right. But I know that lambda is m over L, right? So from here, right, lambda is m over L. So I've got m over L times L squared over 2m. M's cancel out, one of these cancels out, and I get L over 2. That's the location of the center of mass for a uniform rod. It's just right in the middle. Right, but now let's do this a little differently. Now we want to say that there's some constant. That lambda is not just, lambda is not, that we have a function for lambda, okay? Where lambda is equal to alpha x, where alpha is some constant. So again, we have this, that lambda is m over L, all these things. We know that lambda is also equal to alpha x, and I know that m is still equal to lambda L, and I know that dx is equal to lambda dm. Okay, and yeah, so let's go with that for now. So now we've got 1 over x center of mass. It's going to be 1 over big M, integrate from 0 to L of x dm. Okay, but again, dm, this is not in terms of m, so I'm not going to take the antiderivative of that. So now I come back here, 0 to L, x, and instead of dm, I can, whoops, I messed this up. Sorry, dm is equal to lambda dx. So this is going to be x times lambda dx. But now lambda is not constant. In the previous problem, lambda was the same amount of mass per each part of the rod. But now I have a function for lambda. It's alpha x. So I've got 1 over the mass from 0 to L, x times alpha x dx. Right? So simplifying, alpha is a constant, so I bring that out. Alpha over m from 0 to L of x squared dx. All right, notice before we had an x in here, so you might notice a little pattern. This is going to be alpha over m, 1/3 x cubed from 0 to L. And then come up here. So I get alpha over m. This is going to be L cubed over 3. Okay. Now we want to plug in. M. We need to find out what the total mass is. All right. So how do we get that? M is equal to adding up all the tiny little masses. Right. So m is going to be from 0 to L. dm is this thing, lambda dx. But lambda dx is, lambda is alpha x, so alpha x dx. So I end up with, oops, don't need that, just alpha L squared over 2. And then I can plug this in here, because this is what big M is equal to. That's the total mass. All right, so a lot of substituting here. So I have alpha L cubed over 3 divided by M, which is alpha L squared over 2. Alphas cancel out. Some of the L's cancel out. And I'm left with 2L over 3. All right, that's the location of the center of mass, the x coordinate. All right. Notice before it was 1/2 L. Now it's 2L over 3. If you repeat this, and let's say that instead of this being alpha x, let's say it's alpha x cubed. All right. So before it was just constant. Right? Here x, this has an exponent of 1. We end up with 2L over 3. But watch what happens if I change this. I'm going to change this to cubed, alpha x cubed. So what happens is this is alpha x cubed. So this is then x to the 4th, right? Now this is to the 4th, or sorry, 3rd, right, 4th. So this is going to be to the 5th. Right. So let's redo that. We'll get a new thing down here. So this is going to end up being L to the 5th over 5. When I plug this in, if this is to the 3rd, all right, then I'm going to end up with alpha over 3 L cubed. All right. Or L to the 4th, sorry. Alpha over 4 L to the 4th. I plug this in, and I get alpha L to the 5th over 5 over m here. This is alpha over 4 L to the 4th. Alphas cancel out. This cancels out with these, and I'm left with 4L over 5. Right? So first it was 1/2 L. Then it was 2L over 3. Now, right, I skipped an exponent. I skipped x squared, so this is x cubed. Notice now it's 4L over 5. So there's a little bit of a pattern here that you can see. Okay. And then this is an application of surface area mass density. Right? So here we have this triangle, and we're trying to find the x and y locations of the center of mass. It's an area, so we've got 2 dimensions to this thing. Let's take a look. And so what we've got here for the entire sigma, for the whole thing, mass per area, total mass per total area. And what's the area? It's 1/2 base times height, right? So it's 1/2 a times b as we have it in this diagram. So 1/2 ab. Okay, and that simplifies to 2m over ab. All right, but for a piece of it, then sigma is equal to dm dA. Right? And what is the area here? So it's dm. And I've got this split up. I'm taking tiny little pieces of the vertical part, right? So it's y times dx. It's the height of each little rectangle times its width, and its width is a little piece of dx. All right, so here, dm is equal to sigma y dx. Okay, and sigma for the whole thing is this, so this is equal to 2m over ab y dx. All right. Y is a function of x, though. It's linear, right? And so we can find y in terms of x, and we can use similar triangles, right? For any triangle here, we have this is a and this is b, and that's proportional to x and y. So y is equal to, so we'd have like y over x is equal to b over a. So xb or b over a times x, right? So then I plug that into here, and I get 2m over ab times b over a x dx. Simplify further, we get 2m, the b's cancel out, and I'm left with a squared on the bottom, a squared x dx. Okay. So now I get to put all this into the function and find out. So the x, center of mass, 1 over m, and then adding up x dm. But dm is this whole thing, right? So this is 1 over m from 0 to a. Right? I'm going from here all the way for the full length of the triangle. X times 2m over a squared x dx. Okay, so let's get out everything that we can get out here. The m cancels out with the m. I'm left with 2 over a squared, and then in the integral, x squared dx. All right, so 2 over a squared, x cubed over 3 from 0 to a. So that's going to be 2 over a squared, and then a cubed over 3. So I end up with 2/3 of a. And that makes sense, that this is going to be 2/3 of the way down this line. Right? Now that's the x part of the center of mass. Finding the y part of the center of mass is here for you. All right? But the idea is that generally it's going to be 1/3 of the way from the edge of the heavy side, right? So this is 1/3 of the way this way, and then this is going to be 1/3 this way. It's going to end up being 1/3 of b. Okay. And so for a system of particles, let's see what we have here. Looking at the next thing, Newton's second law for a system of particles of total mass m. This works, Newton's second law works also for a whole system of particles. So here we have, right, this is what we're doing now. This is finding the common center of mass, right, the common location. This is finding the velocity, overall velocity. And here this also works for Newton's second law, ma, right? But if I add up ma of each of the particles, then what I'll end up with, adding them all up, is just the net force. Okay, and so that's why we call this is Newton's second law for a system of particles. And so there in that other box on this page, right there, we fill this in. Ma for center of mass is F1 plus F2 plus F3, right, etc. So then A of the center of mass, the acceleration of the center of mass, is 1 over the total mass times the sum of all the forces. And so here we see what we had been using before, that instead of having to take every individual object and analyze all the forces on them and then substitute all the equations, we would look at all of the objects that are part of the system, and if they had a common acceleration, then we could just look at all the external forces and see how they add up. Right. Okay, so here's an example of this. You've got 3 particles that are initially at rest, acted on by external forces as shown in the diagram. Calculate the acceleration of the center of mass of the 3-particle system. So all we have to do here is take the 1 over the total mass. And what is the total mass in this case? It's 16 kilograms. And multiply it by all these forces. Now the forces end up being 6 newtons at 180 degrees. So that is, let's say, negative 6I. And then 12 newtons at 45 degrees. So that's going to be 12 times root 2 over 2 I plus 12 root 2 over 2 J. And then 14 newtons at 0 degrees. So this is going to be plus 14 newtons in the I direction. And then, let's see, this will all just kind of add up here. So negative 6 plus 14 is 8. So we've got 8I plus 12 root 2 over 2I being lazy and not feeling like doing the calculations here, over 16 kilograms. And the units up here are newtons. And so that's it, whatever that adds up to. And we'll just leave it in that form of unit vector notation. Makes it easier that way. Okay. Okay, so in this explosion of a projectile thing, it goes up into the air and it explodes, but it explodes so that mass m falls straight down. And then mass 2m continues on. And what that does is it allows that other mass to go farther than it would have otherwise. So the first thing we do is we use the range formula to find out where the center of mass lands. All right, so R equals v squared sine of 20 over g, v squared sine of 2 theta over g. So that's, we plug our numbers in. V is 10, so 10 sine of 2 theta, so theta in this case is 60, so it's going to be 120 over g. These cancel out, so sine of, oh, this is squared, so I'm left with a 10. This is root 3 over 2, so I end up with 10 root 3 over 2, so let's say 5 root 3. Okay, which is about 8.7 meters. Now, here's my diagram. So here, this full range, all right, and then if I divide that in half, this is 4.35 meters from here to here. Okay. And then what I can do is I can calculate, if this is the center of mass and one object of mass m is here, then I can figure out where on the other side the other piece is, because the center of mass is going to be conserved. So if this is where the center of mass is, I know, so looking at the equation this way, right? X center of mass is 1 over big M, and then adding up each of these locations, right? Mi x1 plus m2 x2, and that's it. There are only two pieces to this. I know this is 3m, and I know that this, let's take this to be that piece. This is just the m, and somewhere over here is going to be 2m. And if I take this as my origin, then, or let's see, what did I decide to do here? Be easier if I just do, oh, okay, so if I take this as the origin, right here, that makes that piece go away. So 1 kilogram times 0 meters, that's easy. And now 2m, so that's 2m times x2, I don't know what that is, but I do know that the center of mass is 4.35. Right. So we're going to be taking 2/3, or 4.35 times 3 divided by 2. So when we solve for x2 this way, we end up with 6.525. That means it's 6.525 from here. So then I add that to this, and that'll give me where it lands from the place it was initially shot. Right? So this 4.35 plus 6.525 comes out to about 10 point something meters or so. Okay. And last example. So we have a man, mass m, suspended from a rope attached to a hot air balloon of mass 2m. If the man climbs up the rope at speed v, what is the velocity of the balloon? Right. So we assume that the balloon is there and the man is there, and relative to the ground, it's not moving. But then the man starts to climb up. Okay. So we got to see what is the velocity of the balloon. And here we can use just conservation of momentum. Right. initially the momentum is 0, and then we've got the balloon and the man. So here the total momentum has to equal 0, but the man has a momentum upwards of mv. And we know the balloon has mass 2m. So that means his upward momentum has to be the same as the downward momentum of the balloon. Right? But if the balloon has mass 2m, then the balloon has to have a velocity of 1/2 in order for the total velocity, the total momentum, to remain 0. Okay. And that's it for this unit.